All right, ladies and gentlemen, this problem is the problem that I had you cross out in your notes because it required the quadratic formula. If you would like to learn how to do this problem, it will be worth extra credit points on your test. So let's get started. Our problem says, given the reaction H2 plus I2 yields 2HI, if 2 moles of H2 and 3 moles of I2 are placed in a 1 liter vessel at 1100 Kelvin, what is the concentration of each gas at equilibrium? And it gives us a Kc value of 25. So this problem gives us some initial amounts of gases that are placed into a container and asks us for equilibrium concentrations. So we will in fact have to do an ice table for this. But what it gives us initially is not actually concentration directly. It gives us a molar amount of H2 and a molar amount of I2, which is not the same thing as concentration, but it does tell us that it's in a 1 liter vessel. So remembering that moles divided by liters is concentration, we can safely say that this is 2.00 molarity and that is 3.00 molarity. Again, because I'm dividing both of those values by 1. So let's put together our ice table. Extend that real quick. Okay, so our initial concentrations are going to go in this top row, just like everything else. We have H2, we have I2, and we have HI. None of the components of this reaction are either a solid or a liquid, so we're not leaving anything out of this ice table. So we start out with 2 molar H2. We start out with 3 molar I2. And we do not start out with any product yet because, again, we're placing reactants into a vessel. So next, what we're going to do is we're going to calculate our change. There is no coefficient in front of either H2 or I2, so we're just going to lose X amount of both of those, but there is a coefficient in front of HI, so we're going to gain 2X of HI. Now for our equilibrium row, we're just going to total these two. And so for H2, we have 2 minus X. For I2, we have 3 minus X. And for HI, we end up with 2X. Now, over here, we have to then take our equilibrium row and we need to plug it into a K expression. So the first thing we have to do is actually write that K expression. So our Kc is going to be equal to our products divided by our reactants. So we have HI on the top. That's going to be raised to the second power. On the bottom, we have both H2 and I2. And now I have stuff in my equilibrium row that I can safely plug into that. So given our Kc value is 25, we're going to say that 25.0 is equal to, on the top we have our 2x squared. And on the bottom, we have our 2 minus x and our 3 minus x. Okay, so now let's talk about our actual K value. This K value is unfortunately not small, which is sad because now we cannot use small x approximation to avoid the polynomial. This is also not a perfect square because on the bottom we don't have 2 minus x twice or 3 minus x twice, we have 2 minus x and 3 minus x, so we cannot simply root the entire thing to avoid that polynomial. And what that means for us is we actually have to use the quadratic formula to solve this. So what we're going to do is we're going to algebraically rearrange this into an ax squared plus bx plus c format so that we can easily use the quadratic formula. So just bear with me as I go through those calculations. All right. So now that I've gone through all those calculations, we now have a format that is easy to use the quadratic formula with, because we have ax squared plus bx plus c, and we can plug that into our quadratic formula, which I'm going to write down over here. All right, so to do this correctly, we are going to end up with two different values of x. And then when we get those two different values of x, we're going to have to pick a value that does not yield a negative concentration, because having a negative concentration is unfortunately impossible. So what I'm going to do is I'm going to set up two different quadratic formula calculations. So this one will be the addition of that b squared minus 4ac term, and the one on the right is going to be the subtraction of it. Okay, so again, what I have set up here is my two possibilities because of that plus or minus term up top. So we're not going to go through the algebraic rearrangement of that formula or anything. I'm just going to tell you what the answers to those two are. For the one on the left with the addition, we get x is equal to 4.29. And on the right, we get that x is equal to 1.67. Okay. So given that information, we need to evaluate which value of x actually makes sense for my equilibrium calculation. And to do that, we have to go back up and we have to look at our equilibrium row. So again, keeping in mind that our values that are possible are 4.29 and 1.67. If I look up here, if I take 2 and subtract 4.29 from that, I end up with a negative value, and that is impossible. If I subtract 4.29 from 3, I also end up with a negative value, and that is again impossible. And what that means is that 4.29 cannot be x, because I cannot end up with a negative concentration. And so that's telling me that this value of x is in fact my possible value that I can plug into my equilibrium row. And so to solve the problem, I just need to do that real quick. My equilibrium row said that my concentration of H2 at equilibrium was equal to 2 minus x, and x is 1.67. So that's going to give me an equilibrium concentration of 0.33 molar for H2. My concentration of I2 at equilibrium was equal to 3 minus x, which gives me a 1.33 molar equilibrium concentration. And finally, my concentration of HI at equilibrium was equal to 2x, so 2 times 1.67. And that is going to give me a 3.34 molar concentration at equilibrium. So for this, using the quadratic formula in ICE tables is not necessarily super difficult, it's just long. And so that's why it's extra credit. Adding to that, you will not see this on the AP test, but if you want to learn how to do it, you can get a couple extra credit points on your test, which is rare for us, so I encourage you to give it a shot. If you have questions, feel free to ask.